Hello and welcome to this new video. So we are now in chapter 2. We'll begin chapter 2 in this video about numerical sequences or complements about numerical sequences. And there will be 4 sections in this chapter. We'll cover in this video the first section about Limsup and liminf. The other 2 sections will be covered in the next video. So what we are going to do here in this section is to generalize the notion of limit when it does not necessarily exist. Okay, so consider an arbitrary sequence xn of real numbers, and to simplify the discussion, we'll assume that xn is bounded. So bounded from above and from below. Okay, we set yn to be the supremum of the set xk, k bigger or equal than n. So it's the supremum of the set xn, xn plus 1, xn plus 2, and so on. Now the fact that xn is bounded means that this set is bounded. So the supremum exists. It's a real number. And now what can we say about this new sequence actually? This sequence actually, we claim that it's non-increasing or decreasing, but not strictly. Okay, how do you know that? The set xn plus 1, xn plus 2, and so on is of course contained in the set xn, xn plus 1, and so on. So they just differ by one term here. So the set actually is decreasing. So the supremum actually, when the set gets bigger, the supremum gets bigger, but the infimum gets smaller. Okay, so when you take the sup of the set is less or equal than the sup of the set. Okay, so but the sup of the set is just yn plus 1, and the sup of the set is yn. So yn plus 1 is less or equal than yn for all n. So this proves that yn is non-increasing. Actually, we cannot say in general that yn plus 1 is strictly less than yn, and we shall see examples now. So we say that it's non-increasing, or we can say decreasing. Okay. Now, the fact that xn is bounded from below implies that yn is also bounded from below, right? Because if xk is bigger than some constant, then the supremum of xk is bigger than the same constant. Okay. So now we have a decreasing sequence which is bounded from below. And you know from a first course in analysis that yn is convergent. And it converges to its infinimum, actually, right? So this limit is called the limit superior of the sequence xn, and it's denoted by lim over line lim of xn, or limsup of xn. Okay, so what do we have? So the limit superior of xn is actually, just read it as in the same order. It's the limit of the supremum of xk, k bigger than n, as n tends to infinity. And the limit is just the inf, because the sequence is decreasing. Okay, so before we continue, let us see some examples. If you consider the alternating sequence -1 to the n. Okay, so yn, I go back to the definition. Yn is the supremum of xk, k bigger or equal than n. But the set now is just formed of -1 and 1. Okay, so this set is finite actually, just contains 2 elements. Okay, remember this is what we call the range of the sequence, but here we start from n, but it doesn't matter actually. So the supremum of the set containing 1 minus 1 is of course 1. Therefore yn is actually constant. Okay, so it's decreasing in the large sense, it's not strictly decreasing. Okay, so, and therefore yn is convergent to 1. Therefore the limsup of xn is 1. Okay, and notice something, that if you take the sequence x2n, the subsequence x2n, it's just 1, 1, 1, 1, 1. So 1 is the limit of a subsequence of xn. Okay, and we shall go back to this later in more generality. Now let's trivial example. consider the sequence that starts with 1 plus 1 half, 2 plus 1 half, 1 plus 1 third, 2 plus 1 third, 1 plus 1 over 4, 2 plus 1 over. So you see the pattern. Of course, you can write a formula for xn if you like, but this is not important. So as long as you understand the pattern here, okay. So mainly we have just two decreasing subsequences actually. One that converges to 1 and the other converges to 2. Okay, but let us go back to the definition and prove that the limsup is 2. Okay, now consider this. We start from n equal 1. So y1 is by definition the supremum. We start from 1 here actually. So this is x1, this is x2. So the supremum of this infinite set is of course 2 plus 1 half, because all other elements are strictly less than 2 plus 1 half. Okay, so it's just the second term. If you move to the second, so y2, we start from the next term, x2, x3, etc. So once again, the sup is 2 plus 1 half. When we move to y3, of course, we start with the third element, so 1 plus 1 third, 2 plus 1 third. So here we see that the sup is 2 plus 1 third. y4, same thing. So you see the pattern. Yn is not strictly decreasing, it's decreasing in the large sense, but this is the pattern. So two equal terms, two consecutive equal terms, and then strictly less. When you move to y5, we obtain 2 plus 1 over 4. So y6 is also 2 plus 1 over 4, and so on. So what is the limit of this sequence yn? You should see that it's 2. So we see that it's decreasing, 2 plus 1 half, 2 plus 1 half, 2 plus, etc. So actually, so we can also find a formula if you like here, but it should be clear that this sequence yn tends to 2. So the limsup of xn is 2, right? And once again, the subsequence x2n converges to 2. So there is a subsequence of xn converging to 2. Okay, so the subsequence obtained by eliminating odd indices. Okay. So you got the idea. Okay. Now remark what happens if xn is unbounded. If xn is unbounded, then the set xk k bigger or equal than n is also unbounded. And we agreed in the first chapter to put the supremum of an unbounded set from above to be plus infinity. So in this case, yn is constant, it's equal to plus infinity. And therefore, we may set limsup of xn equal plus infinity. Okay, so this is the case with the sequence 1, 0, 2, 0, 3, 0, 4, etc. Okay, because we already started. So y1 is actually plus infinity because the supremum of this set of integers is unbounded from above. Okay. Now, in a completely symmetric way, we can define the limit inferior, okay, or liminf. So let us redo the discussion. So take a bounded sequence just for convenience. Otherwise, just to avoid the cases like this, plus infinity and minus infinity. Okay. Okay. Now we take actually, instead of sup, we take the inf. Okay, so this is the infimum of the set xn, xn plus 1, xn plus 2, etc. And now, as you may check, actually, so once again, Zn is well defined. It's a real number because this set is bounded from below, so it has an infimum, which is a real number. Now, here by symmetry, actually, we see that yn is non-decreasing, so it's increasing if you like, but in the large sense. Why? For the same reason. But now, so this set is contained in the set. So the infimum actually is in the reverse order as you obtain. So when the set gets bigger, the infimum gets smaller, right? We already observed that. So actually here, the inf of the set is less than the inf of the set in the reverse order. Okay, so try always to take the example of an interval. When the interval increases, the sup increases, but the inf decreases. Okay, it's more to your left hand. So now we have an increasing sequence, and the assumption that xn is bounded implies that zn is bounded as well from above, actually. Okay? So we have now an increasing sequence which is bounded from above, and therefore it's convergent. And this limit is called the liminf of xn. And of course, since zn is increasing, it converges to its sup, as you know from a first course in calculus. Okay, so in short, the liminf also in the same, you can read it in the same order. Liminf is the limit of the inf, okay, which is also the sup of the inf, okay, because the sequence now is increasing. Okay. So let us revisit the same examples. So if we take the alternating sequence -1 to the n, then okay, for any n, this set here consists of 2 points, 1 and -1. So the inf is -1, and therefore, so here we see that Zn is constant. Okay, so in particular, it's convergent to -1. So the liminf is -1. Okay, and here again we see that there is a subsequence. Okay, converging to -1. It's a constant subsequence, actually. Okay. If we consider the same example before, 1 + 1/2, 2 + 1/2, and so on, and we go to the definition, so here there is a slight difference now because it's not completely symmetric as if we take the same example. Because now, if you consider this set 1 + 1/2, 2 + 1/2, and so on, what is the infimum? You may convince yourself that the infimum is 1, actually. Okay, because it's the biggest lower bound. You can prove that, actually. It's not difficult. We did something similar in the exercise of chapter 1. Okay, and 1 is not a minimum. It's not achieved, unlike the sup, which was a max, actually. Here, the infimum is not achieved because this set does not contain 1. Okay, and therefore, and similarly, Z2 is the same thing. It's 1, actually. So we have, so Zn is constant, and therefore its limit is 1, and therefore the liminf of xn is 1. And we can do a symmetric remark. If xn is unbounded from below, then Zn is -infinity. Okay, because the infimum of an unbounded set from below is -infinity, so it's just a constant. And in this case, you may set liminf. Sorry, there's an error here. Liminf is -infinity. Okay, correct that. Okay. This is, for example, the case of this sequence: -1, 0, -2, 0, -3, 0. Okay, so the inf already, if you take Z1 here, actually the inf, so Z1 is -infinity because okay, so it's constant. The sequence Zn is constant. It's equal to -infinity. Okay, now we move to our main result in this video about some properties of Limsup and liminf. Okay, so we already observed that in the examples that there was always a subsequence of the sequence converging to Limsup and the subsequence converging to liminf. Now, this is not a coincidence. It's a general fact, actually. And in some sense, the Limsup is the biggest element such that there exists a subsequence converging to it. Okay, so this is what we shall explore. But how to? So we give a name to limits of subsequences. Okay, and this is done with the concept of accumulation point of a sequence. Okay, so if xn is a sequence and x is a real number, we say that x is an accumulation point of the sequence if there exists a subsequence x and k that converges to x. Okay, this is the concept of accumulation point. It's actually related to the notion of accumulation point of a set, but they should be distinguished, actually. Okay. So now we are ready to state the main theorem. Okay, so if all sequences are bounded, so in order to avoid plus and minus infinity, the first property states that Limsup and liminf satisfy the same conservation of inequalities as in the limit. So we know that if xn is less than yn and both are convergent, the limit of xn is less than or equal than the limit of yn. But we have more generally the same thing for liminf and limsup. Okay, so you can restate the first property by saying that liminf and limsup conserve inequalities, but in the large sense. Even if xn was strictly less than yn, we cannot say that liminf is strictly less than liminf. Okay, so this is not difficult actually, it takes one line of proof. Second thing, as you expect, the liminf is less or equal than the limsup. Now we may have equality, and this happens if and only if the sequence is actually convergent. So if the sequence, and this is the third property actually, so we have equality in 2 if and only if xn is convergent to the same common value here. So if xn is not convergent, liminf is strictly less than limsup. Okay, so we see here that the concept of limsup and liminf are extensions of or generalization of the notion of a limit. Okay, and fourth property, if xn is non-negative, then saying that xn tends to 0 is the same thing as saying that limsup of xn is 0. And last property, the limsup of xn is the biggest accumulation point of xn, and liminf is the smallest accumulation point of xn. Okay, now some of these properties is very easy to understand. So, but however, 3 and 4 and 5 are a little bit maybe a little bit difficult. So you may skip them safely, but it's important to understand them, okay, and to apply them. So you may skip the proof of 3 and 5, okay, but you should know all these properties. And we shall explore more properties of limsup and liminf in the exercises. Okay, so let us start with the first property. If xk is less than yk for all k bigger or equal than n, then the sup of xk is less than the sup of yk, as you may check. Okay, because if xk is less than yk is less than sup of yk, right? So this is an upper bound. This is the smallest upper bound. So okay, we did something similar. So therefore, and both sequences here are actually increasing. So when you so are convergent because they are decreasing. So when you take the limit, we get the result. The limit of this is by definition the limsup of xn, and the limit of this as n tends to infinity is the limsup of yn. So we get limsup of xn less or equal than limsup of yn. And the proof for liminf is completely similar. Okay, just write inf of xk less than inf of yk, and let n tend to infinity. Okay. Now, second property, why is the liminf less than the limsup? Because the infimum is always less than the supremum, as you know, for any set. So when you let n tend to infinity, you get liminf less than limsup. Okay, so this is very easy. This just follows from the definition. Now, the third property. Okay, we have two directions here. So two implications, if you like. So suppose first that the liminf is equal to the limsup and call this common number small l. We will prove that xn is actually convergent to L by going back to the definition of convergence. Okay, so how do you do that? With the epsilon, with the usual epsilon definition. So let epsilon be given. Okay, now what is L actually? L is the limit of, so if you take actually the sup, okay. Sup xk converges to L, right? So this is by definition, because right. So as n tends to, so what does it mean? So you agree now that sup xk as k bigger for k bigger or equal than n as n tends to infinity, this quantity as n tends to infinity converges to L because limsup of xn is L, right? So this is what we call, this is the sequence that you call yn. Okay, so saying that limsup of xn is L means that the sequence yn converges to L, and this precisely what does it mean? It means that the difference can be made arbitrarily small for n large, say for n bigger than n1, let us say, or n0. Now, so in particular, the supremum of x. So this is yn. So yn is between between L minus epsilon and L plus epsilon. So in particular, sup of xk, this is the yn. Yn is less than L plus epsilon. But who is bigger, xn or supremum of xk, k bigger or equal than n? Of course, the supremum is bigger. So we have a first condition now for n large, and for all n large enough, xn is less than L plus epsilon. Okay, because of this. And I don't need the full strength of this inequality. I just need half of it, because this is a double inequality. Okay, this means, okay. Now, we do the same thing now with the liminf. Okay, so if the liminf is L, it means that the sequence Zn converges to L, as we defined, keeping the same notation. But the sequence Zn is just inf of xk, k is bigger or equal than n. So, and we do the same thing, but with the reverse, the other inequality. So when we say that inf of xk minus L is less than epsilon, it means that infimum of xk minus L is between minus epsilon and plus epsilon. So this sequence Zn actually is bigger than L minus epsilon. Why are we doing this? Because, of course, the inf is less in particular than xn, right? For all n large enough. Okay, so here let us say n bigger than n1, here n is bigger than n2. So in order to obtain both inequalities now, we take n bigger than n1 and n2. So for all n large enough, we have xn is between L minus epsilon and L plus epsilon. Since epsilon was arbitrary, this precisely means that xn converges to L. Okay, because this just means that xn minus L in absolute value is less than epsilon. Okay, so this is one direction, and this is the easiest part actually. So we proved that if the liminf and the limsup are the same, coincide, then the sequence is actually convergent to the same common value. Okay, now the converse. Suppose that xn is convergent to L. We want to prove that limsup equal liminf equal L. Okay. One way of doing this is to prove that the limsup minus L is less than epsilon for every epsilon, right? Because now the limit is constant and the limsup is another constant. Okay, so to prove that A is 0, we prove that absolute value of A is less or equal than epsilon for every epsilon, right? We'll get back to this. So we consider an arbitrary positive number, epsilon. Since the sequence is by assumption converging to L, then there exists a certain rank n0, starting from which the sequence xk is between L minus epsilon and L plus epsilon. Okay, this is the definition. Okay, so now if xk is less than L plus epsilon for all k bigger or equal than n0, and if you take now n bigger than n0, right? So what do we have? We have the supremum of xk, k bigger than n, is less than the supremum of xk, k bigger than n0, right? We already observed that. And the supremum of xk, k bigger than n0 is less or equal than L plus epsilon. This is the property of the supremum. But we cannot write strictly less because you may have equality. Okay, so if you look at this half of the inequality, you will get that supremum of xk, k bigger or equal than n. So this is what we call the yn. So yn is less or equal than L plus epsilon for n bigger or equal than n0. If you look at the second part of the inequality, you will get that the infimum of xk, this is what we call Zn is bigger or equal than L minus epsilon. And of course, Zn is less than yn. So we have this estimate, okay, for n big enough. And now, when n tends to infinity, this sequence converges to liminf, and this sequence converges to limsup, right? So if you just consider the inequality L minus epsilon less than then yn less than L plus epsilon, and let n tend to infinity, you'll get limsup of xn by definition is between L minus epsilon and L plus epsilon. And if you consider this inequality inf or zn between L minus epsilon and L plus epsilon, and you let n tend to infinity, you get liminf of xn is between L minus epsilon and L plus epsilon. So this means that since epsilon was arbitrary, that the limsup is small l and the liminf is small l. Okay? Or if you like, another way of seeing this, since now the limsup of xn does not depend on n, it's a constant. Okay? So we have two constants here. If you like, call this capital L. Capital L is between L minus epsilon and L plus epsilon. And since epsilon was arbitrary, we may let epsilon tend to 0 itself. If we let epsilon tends to 0, this is a constant now, it doesn't depend on epsilon, right? So we get L minus epsilon less than so we get small l less than capital L less than small l. So by the sandwich theorem, we get limsup is equal to L. And you have something similar here. Okay, so this concludes the proof of point 3. Okay, now fourth property, also we have two implications. Xn is by assumption bigger or equal than 0. We have to prove that if the limit of xn is 0, then the limsup is 0. Because this follows from 3, because if the limit exists, it's equal to the limsup and liminf, right? So if the limit is 0, then the limsup is 0, if the limit exists. Okay. So now conversely, suppose that the limsup of xn is 0. Okay. If the limsup is 0 and xn is bigger than 0, then we can conclude that the liminf of xn is greater or equal than 0, right? By going back to the definition. If xn is bigger or equal than 0, then zn is bigger or equal than 0, and so limit of zn is bigger or equal than 0. Okay? So what do we have now? We have liminf less than limsup, which is 0, but liminf is bigger or equal than 0. So we have 0 less or equal than liminf less or equal than limsup equals 0. So all these four quantities are 0. Okay? And now, if limsup equal liminf, then by 3, the sequence is convergent and to the same common value. So this is a useful result in analysis because sometimes we don't know if the sequence has a limit, but it always has a limsup. Okay, so if the limsup is 0, then actually the limit exists and is 0. Okay. Now the last property. Okay, so we'll prove it just for limsup, and we leave the limin for you as an exercise, just completely symmetric actually. But it's a good exercise for you if you can do it, if you write it properly. Okay, so we have to prove two things actually. That the limsup is the limit of a subsequence of the sequence. Okay, and then we prove that it's the biggest one. So two things actually. Okay, so call the limsup capital L. Now here in this case, limit of xn need not exist, but the limsup exists. Okay. Okay, so we go back to the definition. This is what we called yn. Okay, and yn was decreasing actually. So decreasing and converges to its n, which is L. So when we say that yn converges to L, but from above, then yn will be between L and L plus epsilon, right? For n big enough. Okay. Now, by a property of the supremum, when we subtract epsilon from the supremum, it's no longer an upper bound, right? Because this is the smallest upper bound of the set xn plus 1, etc. So we already used this fact several times. So this inequality. So what we are saying is that for every epsilon and for every n, there exists m bigger or equal than n, such that xm is bigger than the sup minus epsilon. Okay, and this just means simply that sup xk minus epsilon is not an upper bound of the set xn plus 1, etc. Okay, therefore we have this condition. If you combine both, okay, now the sup of xk minus epsilon is bigger than L minus epsilon, right? And of course, xm is less than L plus epsilon. Okay. So we have proved this condition. For every epsilon positive and for every n, there exists m bigger or equal than n, such that xm is between L plus epsilon and L minus epsilon. Okay. And this is the key to construct a subsequence that converges to capital L. Okay. If you like, if you recall chapter 1, this is a weaker kind of convergence, because you are not saying there exists n for all m, etc. Okay, this is something weaker. It means that there is infinitely many indices m, such that xm is between L minus epsilon and L plus epsilon. And so what this means is that every neighborhood of L meets the range of the sequence. Okay, so if you like, L is an adherent point to A, to the range, right? Okay. So now we are going to construct a subsequence step by step. First, take epsilon equal 1 and n equal 1. Then we find an m bigger or equal than 1, such that, and call this xk1. So the m, call it k1. So we have xk1 is between L minus epsilon, L minus 1 and L plus 1. Okay? And now take epsilon equal 1/2 and n in the previous condition to be k1 plus 1. Okay? Because I need something strictly increasing. Therefore, there exists m that I call k2, bigger or equal than n, so bigger or equal than k1 plus 1, such that xk2 is between L minus 1/2 and L plus 1/2. And now you probably guessed the continuation. At the first step, I take epsilon equal 1/3 and n equal k2 plus 1. So at the p step, more generally, we get an index kp strictly bigger than the previous index, such that xp is between L minus 1 over p and L plus 1 over p. And now xkp, because by this our choice of the indices, so kp is strictly increasing as a function of p, kp is strictly increasing. So xkp is a subsequence of xn. And by construction, it's between L minus 1 over p and L plus 1 over p. So when p tends to infinity, xkp converges to L. So we have found a subsequence that converges to L. Okay? Now, we just have to prove the final point that for any subsequence, for any convergent subsequence, the limit is less or equal than the limsup. Okay? So consider a subsequence. Now, this is another notation for subsequence. Instead of writing okay, I should have said here x phi k, okay, but when I write x phi n, it's understood this is just another notation for x mn, if you like. So where phi is strictly increasing between the natural integers. Okay, so this is another notation that you find for subsequences. Okay, so if you don't like this notation, don't worry. We'll call it xmk, okay, in order not to confuse the n. So call it xmk if you like. And since it's a subsequence, this mk is bigger or equal than k. We already observed that in the first chapter. Okay. So in particular, the set xmn first term, xmn plus 1, xmn plus 2, etc. is contained in the set xn, xn plus 1, xn plus 2. Right? So this is a subset because it's a subsequence actually. And now when we take the sup, okay, the sup conserves the orientation here. So sup of x phi k for k bigger or equal than n is less or equal than the sup of xk, k bigger or equal than n. Okay, and when we let n to infinity, the first limit will be limsup of x phi n, and the second will be by definition limsup of xn. Okay, but our assumption is that x phi n is convergent, right? Some L. So the limit, so the limsup is just the limit because it's convergent. So the limit of x phi n is less than the limsup of xn. Okay, so we proved that the limsup is the biggest accumulation point of the sequence. Okay, so this concludes the proof of theorem 2.1 and section 2.1. So thank you for your attention, and if you find this proof difficult, don't worry, you can watch it another time, but I will not ask you something very difficult. Okay, so thank you for your attention.